Hi everyone, this is Kostas Kollias with my recorded talk for ITCS 2023 on the paper Online Learning and Bandits with Queried Hints. This is joint work with Aditya Bhaskara of the University of Utah, Sungjin of the University of California-Merced, Sreenivas Gollapudi of Google Research, and Kamesh Munagala of Duke University. So in this work, we study a model for hints for two traditional problems, online linear and convex optimization, and multi-armed bandits. Now let's start by looking at the first problem, online linear optimization. What we have is a bounded decision space, capital D, that has D dimensions. At each time step t, the algorithm will get to choose a decision point x sub t in the decision space. After the algorithm does that, nature will reveal in an adversarial fashion a linear cost vector c of t. The cost that the algorithm incurs is a function of c and x, c of t and x of t. In the linear case, it's the dot product between ct and x of t, but more generally, it can be a convex function. Let's look at an example in this context, online shortest paths. In this case, the decision space is the set of paths between two designated endpoints, S and T, in a graph. The dimension of the problem here is given by the number of edges. At its time step T, the algorithm will pick one path, P of T, and then nature will reveal the edge lengths. The cost that we will incur is the length of the path that we picked in this particular round for the costs that nature gave us. Observe that in this case, the decision space has exponential size, but we can efficiently optimize over it. And you should be thinking of these types of settings for the results that I will mention next. Now, what is the benchmark that we will compare against? What is the metric that we will use? The benchmark is standard best fixed action in hindsight. So overall, the points x in the decision space, the one that minimizes the accumulated cost over the time horizon, capital T. Let's call this opt. The metric we care about is the regret of the algorithm against this opt. So the accumulated cost of the algorithm over all T rounds minus opt. Right. So central results tell us that there exists an algorithm that achieves regret that is order of square root T for this model, and this is the optimal that we can do. However, recently researchers have tried to improve this result by looking at the case of hints given to the algorithm before the decision is made at every round. A hint h of t tells us something about the cost vector c, right? And the motivation behind this is that we have an auxiliary machine learning model that makes a prediction about the cost vector. Right? Now, in this framework, there are three properties that we typically care about. The first one is termed consistency. It means that if the hints are correct, if they're very good, then the regret should be very low or vanish. On the opposite side, we have robustness, which is that if the hints are really bad, then the regret should revert to what we can achieve in the case of no hints. So in this case, it should be order of square root t. Finally, we have the property of weakness, which is coupled with consistency. It says that we want to achieve consistency, but without very strong or explicit hints. Weaker hints should suffice. And again, the goal is to compare against the optimal action in hindsight. Now let's look at what does it mean to have a strong hint or a weak hint. A strong hint is a vector h of t that tries to directly predict the cost vector c of t. And then previous work tells us how the regret goes down as this prediction gets better and better, and it's the expression that you see here on the slide. A weaker hint would be some idea about the direction of c sub t. Right? So ht is a vector such that the dot product with ct is a positive number. Another idea for weak hints is that b of the hints can be completely wrong. All right, and previous work tells us that we can get regret that is order of square root b plus 1 times log t under some restrictions such as the decision space being close to the Euclidean ball. Now let's look at the hint model that we study in this work. We think of it as the algorithm choosing a direction rather than being given a direction, and we also consider the case where b of the hints are completely wrong. So what do we mean by the algorithm choosing a direction? Typically, what happens is that the algorithm picks two decision points rather than one. It passes these 2 points to the auxiliary ML model, which tell us which one of the two is better. So on which direction the algorithm should move. And typically we will play the point given by the auxiliary ML model. Right, so as a preview, the results that we will get is order square root b plus 1 for any bounded decision space in the linear optimization model. This result extends to the case of convex cost functions and convex decision spaces. And later on, for the multi-and bandit setting, when all the hints are correct, we will see that we can obtain regret that is order of log t. All right, now let's start with the linear optimization setting and talk about the algorithm in the analysis. To do so, we will need some components from previous work. So let me go over them first. The first one is follow the leader type algorithms. Follow the leader is an algorithm that looks at the cost accumulated by each action over all previous time steps and playing the action that minimizes that. So it's not hard to see that this will be overfitting to the past. A stronger version of it is the one called Be the Leader, which looks at the cost accumulated over all previous rounds, but including the current one. So this means that it's not something that we can play. It's an infeasible strategy because we don't know the cost of the current round. It's more of a thought experiment. But if we could play that, we would get an algorithm that has zero regret. Now, a middle ground between the two can be achieved using regularization in the sense of summing up the cost vectors observed in all previous rounds and adding some noise to them. If the noise is of the sort of d over eta, where d is the dimension and eta is a parameter, we know that this will increase the regret by an order of 1 over eta. So if we apply this to be the leader, we get be the regularized leader, we will get an order of 1 over eta regret. A second component that we will use is the concept of differentially private noise. So if the noise we add to each dimension is an independent Laplacian, 2d over eta, and we do that on follow the regularized leader, if we apply that on follow the leader, and we get a distribution g of t over possible decision points. We do the same thing on be the leader to get be the regularized leader, which induces a distribution h of t over possible decision points. Differential privacy implies that these two distributions are close pointwise. So for every decision, the probability in one versus the other is within a multiplicative e raised to the eta. Now, given this, let me describe what our algorithm is actually doing. At its time step t, we will draw two samples from the cost vector accumulated up to point t minus 1 plus the Laplacian noise on each one of the dimensions. We will get the optimal decision point for the first cost vector, the optimal decision point for the second cost vector. We will pass them on to the auxiliary ML model. It will tell us which one of the two is best, and we are going to play that. Now, let's think of coupling this algorithm with be the regularized leader. Be the regularized leader draws a sample from the accumulated cost, including the current time point, and adds the Laplacian noise to it. And then this induces a distribution over decision points. Our algorithm draws two samples from the accumulated cost vector up to the previous time point plus the Laplacian noise. And this again induces some distribution over decision points. We can argue that these two distributions, G and H, actually do satisfy eta differential privacy, which means they also satisfy the differential privacy property of the distributions being pointwise within eta, e raised to the eta. And then this brings us to our key lemma, which says that if we have these properties and we choose parameter eta correctly, which in our case means less than 0.4, we will get that the expected cost of our algorithm will be less than or equal to the expected cost of be the regularized leader, which implies a regret of order 1 over eta, which in our case is a constant. Now, considering imperfect hints and the case where B of the hints are wrong, we will assume here that we know B, even though I will note that this assumption can go away with standard doubling tricks and the property that we can observe after each round whether the hint was correct or not. Let's assume for now that we do know this number, P. We need to modify the algorithm a little bit. We will do so by updating parameter eta to be 1 over 5 times square root of b plus 1. And we will introduce a new probability parameter, that is p, which is equal to 5 times eta. The algorithm will again draw two cost vectors with Laplacian noise, find the two optimal decision points for each one of the two vectors. And then what the algorithm will do is query the ML model, but not always play what the ML model says. Play that with the probability p, and play the first decision point with probability 1 minus p. So probability 1 minus p, in some sense, it follows the algorithm follow the regularized leader. This will induce a modification of the key lemma that I mentioned before. And now it becomes that p times the cost of following the hint plus 1 minus p times the cost of doing follow the regularized leader is less than or equal to the cost of be the regularized leader. And then the analysis will, the proof will proceed with a case analysis where we know that on the steps where the hint is correct, we don't incur any additional regret. So we can focus on the B steps where the hint is wrong. And we have two cases. The first one is with probability 1 minus p, where we make the same decision as follow the regularized leader. And we look at the two subcases with probability 1 minus eta. The decision to follow the regularized leader is the same as be the regularized leader, so no additional regret incurred. So with the remaining probability eta, we have a regret per time step that is constant. So we get a total regret of order of b times eta, which is with the choices of our parameters square root of b plus 1. And the second case with probability p, we actually use the wrong hint, and the regret per step is constant for these steps. So we get a total regret of b times p, order of b times p, which again comes out to square root of b plus 1 for the parameters that we have chosen. So this wraps up the first setting, and we move on to the case of multi-armed bandits. In multi-armed bandits, we have n arms that we have to pick one in every round. The differences from the previous setting is that now first of all, let's switch to rewards rather than costs for this setting. Now, the rewards here are not chosen adversarially. They come from unknown distributions, one for each arm. These distributions are independent, and we will write mu I for the mean of distribution I and sigma I squared for its variance. The second difference is that once we play an arm at a given time step, we only get to observe the reward for that particular arm and not for the others. Again, the benchmark that we compare against is the optimal action, the optimal fixed action, the reward of which in this case can be written as t times mu star, where t is the time horizon and mu star is the optimal mean. Now, here classical results tell us that the best we can achieve is order of square root n times t. Now, the hint model is very similar to the one we saw in the previous section. At time t, the algorithm gets to pick two arms, A and B. We ask the ML model which one of the two is best, we get a response, and we play that arm. Here we will assume that the hints will be correct in every round, and again we will try to match we will compare against the benchmark of the optimal fixed action. The result that we will get is that the regret will be of the order of n squared times log t, so we get exponentially better dependence on the time horizon. Now, again, before I define the algorithm, I'll give you some components that we will use. In this case, it will be the UCBV algorithm, which maintains over its run for every arm the number of times that it has been played, S I of t. The mean of the samples we have observed, M I of t, and the variance that we have observed, V I of t squared. Given all these, UCBV defines a score on the arms, which is pretty much the mean plus an optimism parameter, which is higher for higher variance and higher for arms that have been played fewer times. Yeah. Now, to analyze the regret of UCBV, we need to define capital R of I, which is the expected regret we will get over the run of the algorithm by playing arm I, and capital delta of I, which is the difference between the mean of this arm and the mean of the optimal arm, from mu star minus mu I. Now, we know from previous work that the regret we will get on arm I will be given by this expression, so 10 times the variance over the difference from the best arm plus 1 times log t. So we get lower regret if the arm has smaller variance, and we get higher regret if the arm is close to mu star, because it will be played more times. All right, now let's see how our algorithm works and how its analysis proceeds. Our algorithm will be defined on meta arms. So on pairs of arms, we get each pair of possible arms, and we call it meta arm in this case, and we will run UCBV on the meta arms. So if meta arm I comma j is the one that has the highest score at time t, we will query the ML model, give the two arms I and j, and we will ask which one of the two is better. So the reward for these meta arms follow the distribution that is the maximum of the two distributions between the two arms. And then we can define the new ij to be the mean of this distribution. Now, to look at the analysis, we will define capital M star, which is the maximum, which is pretty much the mean of the best meta arm. And we will have capital delta ij, which is similar to what we had before for the single arms, the difference between a meta arm and the optimal meta arm. Now, the regret will be measured, the regret capital I of j will be measured against M star, so the optimal meta arm, which, as you can understand, as you see here from the picture, is better than the best fixed arm, because the optimal meta arm can have the best fixed arm and something else, which this something else can be better than the arm that has the maximum mu star in some of the rounds. So the meta arm can get something higher than the best fixed arm. Now, if we just plug in these values on the result for UCBV, we get this expression here at the bottom. And now this brings us to our key lemma, which in this case says that for meta arms that have mean rewards lower than the optimal single arm, then their difference, capital delta ij, from the optimal meta arm is greater than or equal to their variance divided by 4. Right? So given this technical lemma, if we plug it into the theorem for UCBV, you will see that the dependence on the variance and the capital delta vanishes, and we get that the regret of a given meta arm is at most order of log t. If we sum that over all the meta arms that are worse than the optimal single arm, we get that the reward will be at most n squared log t. Obviously, any other meta arm will not incur any regret. It will be better than the optimal fixed action. So now I will mention one other setting that we considered in this paper very briefly, and move on to conclusions and open questions. The model is called the all-probe query model. The difference from what we saw in the previous model for multi-arm bandits is that we will play k arms, like more general than just two, let's say k arms. And we will get as a hint the reward of all the k arms that we played, rather than just the one that we will pick in the end. Okay, of course, we will play the one that is best, but we will get feedback for all the k arms that we picked. Again, comparing against the same benchmark as before, the results that we get is that if we can play 3 arms, k equals 3, then we can achieve a regret that is order of n squared. So it has no dependence on the time horizon. And Finally, if the rewards are independent across time like before, but the arms are correlated with each other, then if we can play 4 arms, we will get a regret that is of the order of n raised to the 8 over 3 times t raised to the 1 over 3. All right, so now to conclude, what we saw here is that this model of queried hints, they are weak in the sense of the definition that I mentioned before, but they are also powerful hints that can leverage existing results in interesting ways and improve them. Now, in terms of open questions that follow from this work, first one would be to tighten the results we got on the bandit problems. Maybe you realized, I mentioned at some point that meta arms can be better than the best single arm, so regret can become negative, and we're not using this in the analysis. And can we get, another question is, can we get similar improvements for the adversarial bandit setting, as opposed to the stochastic one that we use here? Finally, can results be extended to the contextual bandit setting? And more generally, can this model of queried hints be applied to other online problems? So I would encourage you to read the paper and look at these open questions. And thank you so much for listening. I hope you have a good time at the conference.